Okay, this is the second video for this unit. We're going to be resolving vectors. And we talked about this a little bit in class. When we resolve a vector, we're going to break it. So to resolve, it's the term we're going to use a lot. It means that we're going to break the vector into its x and y components. Basically, we're going to take a vector and figure out which part of that vector is in the x direction and which part of that vector is in the y direction. So, taking a vector, breaking it into its x components and y components, the x part and the y part. And the whole goal here is so that we can add them all together and figure out a result. So, we're going to take two vectors, resolve them, then add them together. So, the first one, resolve the following vector. We have 50 meters at 30 degrees. So, the first thing that I like to do anytime I get a vector, even though we're not doing the graphical method, here's the steps that I usually go through when I resolve a single vector. One, I draw a picture. Super helpful. Lets you see where things are. Two, I identify the x and y directions as opposite or adjacent to the angle that we're given. And three, I'll use sine and cosine to find the magnitude of the x and y components. Now, let's draw this thing. So, there's my 0, I go up 30 degrees, and I draw my vector 50 meters long. It doesn't have to be exact. This is just a sketch so I can see where things are. So, I need to look at the x and see where that is, and then the y and see where that is. Then we're going to label them as opposite, adjacent, and hypotenuse. So that y is opposite my 30-degree angle. X is adjacent to my 30-degree angle, and the hypotenuse is 50 meters. I'm not sure I spelled hypotenuse right. I don't think it matters. So, if we're going to start with the y, okay, I have the opposite and the hypotenuse. That means I'm going to be looking at the sine of that 30-degree angle. The sine of that 30-degree angle is a number. Sine of 30 degrees is just the ratio of the opposite side over the hypotenuse of all 30-degree angles everywhere. Any triangle, any right triangle with a 30-degree angle in it, if you take the opposite side, divide it by the hypotenuse, you will always get the same thing. And so the sine of 30 degrees, or the sine of any number, or the cosine of any angle, is going to be just a number. So let's look at what that just a number is. I have 50 meters. Since it's just a number, the only thing we don't know in that expression is y. So we'll multiply both sides of the expression by 50, and then we'll plug some numbers in and calculate y. So that gives me 50 meters times sine 30 equals y. Well, that's 50 meters, and then in your calculator, if you do sine 30, you get 50 meters times 0.5 is equal to y. Calculate it out, and my y component is 25 meters. I need that. And then we'll do the x part. Looking at the x, that's my adjacent sine. So we're going to use cosine of 30. So the cosine of 30 degrees is equal to x, my adjacent side, over my hypotenuse, which is 50 meters. So multiply both sides by 50. I have 50 meters times the cosine of 30 equals x. So 50 meters times, and the cosine of 30 is 0.866. That tells me that x is equal to 43.3 meters. So what we've done here, just to sketch it out real quick, so we've taken this 50-meter thing, and we've looked at how much of that's in the x, which is 43.3 meters, and how much of that's in the y. 25 meters. So when we start adding these up, I would put in my y column positive 25 meters and in my x column positive 43.3 meters. So the next one that we're going to look at, to resolve this next vector, is going to be 100 meters at 135 degrees. So we're going to sketch it out. So we got our 100 meters, and it's 135 degrees. That means we go 90, and then we have 45 degrees left. So that's 135 degrees, and that makes the leftover part 45 degrees. So we identify our x, that points over, and the y, that points up. So we have an angle, we have a hypotenuse, we have two sides. So the sine of 45 degrees is going to be the opposite y. So sine of 45 is the opposite y over 100 meters. So we multiply both sides by 100, and we have 100 sine 45 equals y. Plug that into the calculator, and we get y equals 70.7 meters. And since the y is pointing up, it points to the north, so that's 70.7 meters in the y direction is positive. Now we're going to look at the cosine of that angle. The cosine of 45 is x, my adjacent side, over 100 meters. Multiply both sides by 100. Plug that into the calculator, and we see that our x comes out to be also 70.7 meters. But this x stuff points west, which makes it negative. We have negative 70.7 meters. So I've got my y and x components of these two things. So let's call them A and B. And a typical problem would look something like, to add A and B, if I were to add them together, the problem would probably say a man walks 50 meters at 30 degrees, then 100 meters at 145 degrees. What is his resultant displacement? So, we've already resolved A and B. That's our first step for a big problem like this. Now we're going to add the x all together and the y's all together. So looking at the x's, we have 43.3, which is positive because it points to the east, minus 70.7. So my total in the x is negative 27.4 meters. We're going to do the same thing in the y. From the first vector, we have positive 25 meters. From the second vector, we have positive 70.7 meters. We add those two things together, and our total comes out to be 95.7. The last thing that we're going to do is find the resultant by adding these x's and y's together with our little triangle. So it looks like 27.4 to the west and 95.7 to the north. And the resultant is going to be the hypotenuse of that little triangle. So the square root of 27.4 squared plus 95.7 squared. When you put that into your calculator, it comes out to be 99.5 meters. Then we have to find the angle. So that's where my angle is going to be. So the tangent of that angle, I know my opposite side is 95.7. My adjacent side is 27.4. And so when we do the second tan, or tan negative 1, inverse tangent, arctangent, of 95.7 divided by 27.4, that angle comes out to be 74 degrees. Now, we're measuring all of our angles from due east, or that zero line. So really, I have to go 90 degrees and then 74 degrees. So to report this whole thing, sorry, strike that. That's 74 degrees from west. From east is going to be 180 minus that. So the angle that we report needs to be 106 degrees, not 74 degrees. We have to do all of our angles from 0, and we will talk more about this. This is resolving vectors. This is how we're going to break them up into their x and y components. We will practice that tomorrow. Now, the next thing that we're going to do is combining vectors, just looking at different ways to combine them. We're going to do it with velocity this time. So we're combining velocity vectors. The first thing that we're going to do is finding resultant velocity. Now, we've been finding resultant displacement, and all finding the resultant means is that we are adding velocities together. So, a little too far. Sorry about that. Let's speed this up. I made a mistake there. So, finding velocity vectors. We're finding the resultant, which means we are adding them together. So, when we add them together, here's what a problem like that would look like. A swimmer has a speed of 16 meters per second. And he points himself straight across a 64-meter wide river. The river has an easterly current, points to the east, of 12 meters per second. And I want to know his resultant velocity from this. I find it easy to draw a sketch. So we have a little river. It's 64 meters wide. The velocity of that river, the velocity of the current, that's what we're going to call it, is 12 meters per second. Sorry about that, and points that way. The swimmer's velocity is 16 meters per second, and it points up. He's a very fast swimmer. And so what we're going to do is add the 16 meters per second to the 12 meters per second. Like this. We're going to draw those two velocity vectors tip to tail to one another. And the resultant velocity is going to be the hypotenuse of that angle. So, to find the resultant velocity, we're going to do Pythagorean theorem, 12 squared plus 16 squared. When we do that, we get the resultant velocity to be 20 meters per second. But that's not my answer. That's really just the speed part. That's the magnitude. We need the direction. You need to tell me that direction. So, we want that angle. For that angle, the tangent of that angle is 16 over 12. Because the opposite side to that angle is 16 high. The adjacent side is 12 long. So that angle is tan negative 1, 16 over 12. That makes that angle 53 degrees. Remember, we're always reporting that angle from due east. That's why we had to find that angle. Okay? So, when we do things like this, because it's velocity and distance, we can ask and answer some other questions. One question I might ask you is how long, so the resultant velocity is 20 meters per second at 53 degrees. One question we might ask is how long does it take to cross? So, crossing is a y direction question. It's how long to go from one bank to the other. That's all y motion. So when we look at answering this question, we need to look at y information. So in the y direction, I have a velocity of 16 meters per second. I know that's in the y direction because that's the way it's pointing. I have a delta y of 64 meters. And again, that's how far in the y we would have to cross. So my time is going to be my delta y over my velocity, or 64 meters divided by 16 seconds. That time comes out to be 4 seconds. Another question we might ask is, how far downstream did we go? Well, downstream is an X question. So we need to look at our X information. The velocity I have in the X direction is the velocity of the current. That's 12 meters per second. And my time is 4 seconds. So my delta X is my velocity times my time. 12 meters times 4 seconds. 12 meters per second times 4 seconds. Or 48 meters, and that's directly to the east. That's how far downstream we go. Another type of question we might ask that's a little bit difficult is, in what direction would the swimmer have to point himself, would the man, point himself to cross in a straight line? The straight line thing is very important. That means when our guy goes across the stream, he doesn't want to float downstream. So we know intuitively that he's going to have to take his 16 meters per second and point it up. He's going to have to take his 16 meters per second and point it into that 12 meters per second just a little bit. So the way we look at this, we have 12 meters per second from the current, and we want our resultant to be along this straight line. So we're going to have to take our 16 meters per second and point it that way. In this case, 16 meters per second is my hypotenuse. 12 meters per second is my opposite side. That's important. So if we're trying to find that angle, and again, when I ask you for a direction, I need the actual angle. That 12 meters per second is my opposite side. 16 meters per second is my hypotenuse. So to find that angle, we'll be using sine and not tangent. The sine of this angle is 12 over 16 because 16 is the hypotenuse there. So that angle is sine -1 of 12 over 16. And when we calculate it, that angle comes out to be 48.6 degrees. That's the direction we'd have to point ourselves. But 48.6 isn't right because we're measuring everything from east. So we'd have to add 90 degrees to that. And so the direction at the end of everything is 138.6 degrees. I'm going to be kind of lenient on this for a little bit, but eventually all your things need to be measured from that angle. Now, there's one more way that we're going to combine velocity vectors. All right, so this time when we combine our velocity vectors, we're going to do something different. What we're looking at now is finding the change in velocity between two vectors. When we do change in velocity, we're subtracting. Because if you remember, the change in a quantity is the final value minus the initial value. So we're looking at a change in velocity. So here's the kind of thing that we would ask that for. A man driving at 30 meters per second south turns left and is now driving at 40 meters per second east. What is his change in velocity? So, for change in velocity, delta V, change in velocity, is the final velocity minus the initial velocity. So let's plug those in. My final velocity is 40 meters per second east, minus my initial velocity of 40 meters per second south. I cannot just subtract those two and say that my change in velocity is 0. These are two vectors at 90 degrees to each other. You can never say that they are equal to 0 because you cannot just add them together. They cannot just subtract them. And the reason is they're 90 degrees. When we look at those vectors, we have 40 meters per second to the east, and we're subtracting a vector that points in the opposite direction, to the south. We're going to have to use this vector adding tip to tail thing to put them together. But we only talked about adding vectors. So this negative sign here indicates it's the opposite direction. Because of that, it's going to be 40 meters per second north. Okay? That changes how we add the two things together. So by applying that negative sign, by taking the opposite of that vector, it turns into 40 meters per second east, as shown, plus 40 meters per second north. So when we put them together, that's 40 over 40 up, and then we have our resultant. That is our change in velocity right there. So doing the math that we've already worked on, that comes out to be 56.6 meters per second at 45 degrees. We're going to have time to practice all of this tomorrow. I'm sorry that I jammed so much into a video.